Good afternoon, everybody. Well, I have three announcements. First, who is going to do the lab tomorrow? When you do the short circuit test, try not to exceed the current. Look at the current. You don't care about the voltage. Increase the voltage gradually in short circuit test, and try to make the amp about 0.3 amp. Don't exceed that. You are going to get the same result. Why? Because whatever the current in short circuit test, you try to measure the equivalent impedance. So if you make short circuit and you have Z equivalent 1, V1, I1, so Z equivalent 1 is equal the ratio between the voltage and the current. So it doesn't matter. If you have 100 voltage, you will have, for example, 10 amp, you get 10 ohm. If you have 10 voltage, you get 1 amp, you get 10 ohm. So you will get the right result. So don't worry about it. But just to make sure, because the first group, when they exceed the current, I think it exceeds the rating value of the transformer, not the other components. So try to make the short circuit current does not exceed 0.3 amp. Okay, that's the first thing. Second thing, I did the model answer for the last quiz. It's very important about the transformer, and I'm sure after that you have questions. And also I figured out how I can let you go through your exam or quiz, anything I figured out. So I will make it available tonight for you using a submission view item. I tried with one student and it was fine. So from now on, everything will be available after the exam or the quiz. It'll be available for you. You can go and look at your answer. Yeah, I did it last night. Yes. Oh. Yeah. When you go to the folio system and you go to the content of the course, there's a quiz. I always put the keys. You'll find quiz 2 online. That will find the key. And the third thing, try to finish the attendance in 15 minutes, and I want to get it here because I want to make sure that everybody attended here. I don't make fair, Somebody come early, somebody come after 20 to 30 minutes. So I want to make sure that only people they sign the attendance, at least they came in the first 10 minutes. Okay. Do you have any questions? No question. Okay. So let me just go over quickly what I did last time, and then I continue. What we did last time, we try to find the force produced by electromechanical system depend on the coupling field. So simply what we did, we said that that's the magnetic field or the coupling field, all right? And we assume it's lossless, or the energy we're going to talk about now, we are ignoring the loss because it's not big. So what you get from here, that's the energy from the electricity or electrical energy, all right? And what you get from the other side, so you can say that this terminal is the electric side or coming from electric system. And here you go to the mechanical system. So what you get force, all right, and displacement. So that's what you get, all right. How you calculate that? It's related to the field. It's related to the energy stored in the coupling field. That's what produced. And we also said that to calculate the energy, we said that we have the relationship between the current and the flux length. And remember, flux length lambda, we know it's equal N times phi. The total flux linking with the whole number of turns N. And generally, it's nonlinear. It's like the hysteresis characteristic here. So maybe the first portion is linear and then start to bend when you are using iron core. But for air, it has only mu naught, and it's considered to be linear. So we have two cases. We work in general case if it has linear portion and then saturated, so it's nonlinear in general. So if you want to find the energy of the field and the coenergy at this point, we said that if you are going to find the energy in the field, you find this area, this green area. And we call this area the WF, and you are integrating with respect to lambda axis. So the field, or stored energy in the field, coupling field, it's equal to the integration of I d lambda. And the other area, let's just give it a orange color here. This area, we call it coenergy, and call it W. See, in other textbooks, in many textbooks, they will use WF dash, but I just would like, use with the name you remember. That's coenergy. That's coenergy field. How you get it? If you got the area of the box, we said the area of the box is lambda I, so WC could be equal to, you got two options. It's either an integration lambda with respect to I, or the total energy minus WF. You have two ways. All right. How did we find the force? We used two formulas. One related to WF and one related to WC. And the difference between both, the independent variable, we said, is it related to flux linkage or current? So the force equal to, let me make it clear. The force, when you get it related to, or the independent variable lambda x, how you get it, that will be the integration of, the differentiation of WF lambda x with respect to x, and you have a negative sign here to make it simple. This is the force in general. So that's one formula. Use this formula. F lambda is independent variable. The other option, when you have current as independent variable, you can get the same force by differentiating WC, which is function of I and X with respect to X. That will give you the force. So you got two options, this or that, and both they give the same answer. So that's what we did last time. And we did example for how to find the force. Yeah. Let me take another example. Similar to what we did. If we say that the current is equal to lambda square x square 10. Make it simple like that. Or no, just let's make it, okay. 9. That's the relationship between the current and the lambda. You might ask why I or lambda will be function of x2. Let me refresh your memory. The relationship between the current and lambda, let's say that we're taking this one. This was measured at certain gap or certain x. What's x? If you have this electromagnet and you have the movable, or the one that can move, so you have gap here. So that's x. According to x, the gap you're leaving, the flux will change because the flux has to go through the whole thing. If you have the winding, so you have flux going here. That's the flux. This flux, of course, coming from where? From the winding. And this is the source. So that the current go in the winding and reduce flux, the flux crossing the gap. And we know that the flux density is really high or big in the gap. So it depends on the gap. Every time you're changing the gap, the flux. So if you have this at x1 and you want to do another curve at x2, you get another curve. So the flux change with the displacement between the stationary member and the movable one. when you make it smaller, or why? Because it will affect the reluctance. If you want to know why, what's reluctance? Reluctance is equal L over mu A. And we know that the reluctance of air gap Rg is equal Lg, Ag mu naught only. And if you have the core, will be R core, I mean, I'm talking the iron core, will have Lc divided by mu naught mu Rag. What is the difference between both reluctance? You got to understand. Mu R, you are talking about order of 1,000, 2,000, 3,000, 4,000. So what do you expect? I'm expecting the mu of mobility of the iron core is much higher. So you can, if you call this all mu C, for example, so we'll say that mu C is really much higher or greater than mu naught. So if this one is high and this one is low, so what do you expect? You expect that the reluctance of Rg is much bigger than the reluctance of the core. Okay, so that's really the effective part. So changing the X, changing the air gap, and it's an order of millimeter. It affects the flux in the system. So that's why you focus on the air gap. And when you change when you change the L, you are changing reluctance, you're changing flux. So you have lambda also change. That's why for every X, there is lambda for it. So what I sketch here or plot here, it's at certain displacement. So that's why when you write WF or WC, function of I or lambda and X. All right. Well, let's now go to this problem. The relationship between the current is proportional to what? The flux and the displacement X. Now we understand why. We need to find the force when find the force acting upon, let's say that's member A and that's member B, acting on member, acting upon member B. And by the way, this is like the theory of linear electric motor. We didn't talk yet about the rotation. Is it important? Oh my gosh, that's very important. Did you hear about the train in Japan or Germany that the speed is really high? It doesn't touch the floor. Just there is a space between the train. I'll go to you one time video for that. Between the train itself, the body of the train, and the rail that never touch the train. It's by magnetic field elevated. So there is no friction. And use superconductor. The current is high and just fly like an airplane. What is that? It's electric motor. It's linear electric motor. All right. So now let's just find the force. I'm going to use both formula here. I'm going to use one time with WF and one time with WG. Let's just try first WF, which is the energy stored in the coupling field. So I will say that the force, I know the force is equal minus the differentiation of the field stored in the coupling field. It's Wx, and I'm going to use it lambda. That's, I mean, one option. All right. So first, I have to find lambda. But given I was given in this example equal 9 lambda square x squared. That's when they did the experiment, they found that's the relation. So I have to find lambda. So lambda will be equal to the square root of I divided by 9 x squared. So it will equal the square root of I divided by 3x. So you can say lambda is equal to 1 over 3x I power half. That's lambda. Okay. I need to find what, according to this formula I'm going to use, I need to find WF, the stored energy. how can you find the stored energy? I just review with you. To find the stored energy WF, you just have to do the integration I with respect to d lambda. And that's what I'm going to do. So I equal to, I'm sorry, not I, WF equal to the integration of I d lambda equal the integration I is given here 9 lambda square x square dx. I mean d lambda, sorry, d lambda. That's according to this formula. I'll get 9 as a constant, x squared as a constant with respect to d lambda. And then I will have what's left, the integration of lambda squared with d lambda. It's equal to 9x squared lambda cubed over 3. Okay, in this problem, it was given to find the force. Find the force acting on member B at the following condition. When the current, when I equal 4 amp and X, which is the air gap, equal to 5 millimeter. Because the force is, it depends on the magnitude of the current. Why? Because if you increase the current, obviously you're going to increase the force. You're going to increase the magnetic field strength. So it means the attraction and the repulsion will be high. That's number one. And the air gap, it depends. Are you gap far or small? Obviously, when it's small, the attraction will be higher. So it depends on X. It depends on current. It makes sense. So you should define what value of current in the winding and what was the distance that you want to calculate the force at. Depends. So they give me I 4M and X 5M. Now I got the formula for WF. Why? We got the formula for the stored energy because I want to find the force. So the force equal the differentiation of WF with respect to X and negative sign. All right. So I'll say now the force is equal to minus the differentiation of WF over WX. So let's differentiate 9 over 3. Oh, we should simplify it first. That you can say is equal to 9 over 3 is equal 3 x squared lambda squared. So 3 is a constant minus 3 is a constant. You are differentiating with respect to X. So lambda will be constant with respect to that. And what's left X squared? What's the differentiation of X squared? It's equal to 2X. So the answer would be negative 6x lambda cubed. What is that? We got formula for this problem that depends on the value of X and the value of lambda. Can you find now the magnitude of the force at the specific value 4M and 5 millimeter air gap? Yes. But I mean, you have lambda. We don't have I. Well, but you have the relationship between the current and the lambda. You just replace lambda by I. And that's why I got it here. Lambda is equal 1 over 3xi square root. So that's what I'm going to do. Another way, if you want to keep this one, that's okay. We need, okay, let's just write, we need to find the force at I equal 4M and X is equal 5 millimeter. All right. And your formula or the equation you just derive is function of lambda. So you can find the corresponding lambda from I. When I equal 4M, what's the lambda? Corresponding to lambda. According to the relationship, lambda is equal to, so we'll say that find the corresponding lambda. Well, lambda is equal to, that's I'm going to use, just we would write 1 over 3x square root of I. So you have 1 over 3. Okay, well, we're done it. Just I want to plug this one now in this lambda to get the force. So now we have the force Force is equal to negative 6x lambda cubed. So I will make cube this one. So lambda cube will be equal to, if this I power half, so I 3 over 2. And you have 3 times 3 times 3, that's 27, and x cubed. So I got lambda cube. I replace it in this equation. So you have I 3 over 2. And then on the bottom, you get 27 x cubed. Simplify, minus, by 3 is 2, by 3 is 9. And then you have x and x cubed, you have x squared on the bottom. And just leave this one. This is like something like that. Now I can find the magnitude of the force. So the magnitude of the force will be equal to negative 2 over 9, and the current is equal 4. So that will be, okay, maybe I will just do that like I find the 4 square, and then I cube. That will be easier. The same thing, 2 over 3, doesn't matter. And x is equal 5 millimeter will be 5 times 10 minus 3 square. Oh, it should be meter, and that's millimeter. All right. So now I'll just do, if you just can help me get the calculation, you know, that's, I mean, the value we're going to get. That will be 2 cube, be 8, and that will be 5, be 25 times 10 minus 6. So if you can simplify, that'd be great. It's equal minus 16 over 9, 25, 10 minus 6. That will be the force. I think, if I didn't make a mistake, mathematical mistake. Okay. So that will be the solution for the force using this equation. This one, minus WF over dx. You can do it using the other form. The other formula says that the force is equal to the differentiation of WC, and this is function of current, over Wx. So now, instead of finding WF, well, we'll try to find WC. What's WC? You have two ways. I just reviewed with you. WC, you can get it here, either by integrating lambda with respect to the GI, or if you have WF ready, you multiply lambda I. What's lambda I? Lambda I is the area of the whole box, rectangle, as explained last time. The total area of this box, that's, I mean, I, and that's the height equal lambda. It's a rectangle. The area, total area, lambda I. You subtract the area of rectangle minus this green area, you get the orange area. So you have, or you integrate this one. So you got two options. Let me write both options. How to find WC? You got, it's either you integrate lambda with respect to di, and you might ask which one would be better to use. Well, whatever available for you. For example, if you have expression of lambda ready for you, you just integrate it. If lambda given as a function of I, what do you have here? Originally, the problem, I was given a function of lambda. Lambda was not ready. I did it here, but I mean, I was given. That's why I used that. Well, so since you are going to make integration again, no. If you really did get WF, that's WF. So multiply lambda times I and subtract. That's the other thing. Lambda I minus WF. Lambda times I. Let me go back. That's I. 9 lambda square x squared. So I, that's lambda, and I is equal 9 x squared lambda squared minus WF. WF, we got it here. 3x squared lambda cube. 3x squared lambda cube. And you will simplify being 9x squared lambda cube minus 3x squared lambda cube equal to 6x squared lambda cube. That will be the WC. And then what we'll do, here we have the formula. You differentiate that with respect to delta x, and then substitute by the value of I or lambda, whatever corresponding with the x, the same procedure. So I'll leave that to you. It's just the same thing. The same thing. Differentiates easy, something easy, not complicated. So that's how you find the force using WF, the stored energy, and the co-energy. Okay. Any question on that? Yes. Okay. Force. That's not much. Everything in this universe, I said, you follow the same rule. You always try. That's the universe. Try to resist the change. Even human beings, in the beginning, they always try to force any change, just any creature, anything in the universe. So what's happening now when the electro or the magnetic field going and start to change the position of it? So that means this force is acting up to minimize the change. Doesn't mean the negative. So if it's trying to get the moving part, trying to get closer, it will make the force will make it like trying to minimize x to get less. And if it was like in the direction of the current, making the moving part to go out, the force will be in the other direction to push it in. So that's mean opposing the displacement. Yeah, good question. Any question? All right. Now I will go for a special case. The special case is what's happened if we just did it in general. What's happened if you have a linear relationship, or you are operating on the linear region of the flux with the current? And actually, it's very practical, because if you consider the air gap, only the air gap is just linear, all right? So now we are going to work on the linear magnetic system. In the linear magnetic system, we'll assume relationship is linear. So let me just sketch. That's the current, and that's flux linkage, and we'll say that's linear. All right. And in this case, if you want to find the stored energy and the coenergy, so that will be the WF and that will be the coenergy. That's WF and that's WF. And this is like a certain value of current, that's a certain value of lambda. So we know that WF is equal to the integration of I d lambda. But since this straight line, you can find the relationship between lambda and I as straight line equation. So actually you can write like that: lambda is equal to L of X times I. The relationship between lambda and I is the inductance L. Why I write L function of X? Because you can plot many straight lines according to the X. It is a function of X. So that's the relationship between the lambda and I. One's relationship. The slope of this straight line is L, is the inductance. So now I will try to find lambda F will be the integration of I d lambda. So what's I? I will be equal lambda divided by L d lambda. Since I'm integrating with respect to lambda, 1 over Lx will be constant with respect to lambda. So I integrate lambda d lambda. What you get? Lambda squared over 2. So you have you have lambda squared on the top divided by 2 L of X. So that's WF. So we got the expression here. That's what, let's put it there. WF is equal to lambda squared over 2 L of X. Right. What is the goal? The objective. I'm trying to find the force. That's all what we're doing in electromechanical devices. Trying to find the force. So let's drive a formula for the force in the linear magnetic system. Force, now, I mean, remember it's equal the differentiation of WF. And by the way, we just have to remind ourselves function of lambda with respect to x. So I'm going to differentiate WF here with respect to x. So you will have lambda squared constant with respect to x over 2, and then you differentiate 1 over L of x. Let me remind you by differentiation. If I ask you what's the differentiation of 1 over y, it's equal negative the differentiation of dy by dx over y squared. Remember that, right? If you don't remember, just tell me. You don't remember, and I will review it. Do you remember that, or you don't? You don't. Okay, let's review. Okay, I like having that. Yeah. So let's say that z is equal to 1 over y of x, and you want to find dz by dx, differential with dx. So according to the rule of differentiation, if you have a over b, z dash will be equal to differentiation of the top, a dash, times the bottom, minus a times the differentiation of the bottom, divided by the square of the bottom. Definition of a rational, right? Do you know that? Do you know that or not? Yes or no? Yes. All right. Now, if you have a equal 1, constant. So what's the definition of constant? 0. If a equal, so now when you have z equal 1 over b, so it means a dash is equal 0. So let's just substitute. A dash will be equal 0. This term is gone. Minus ab a and a equal 1. So you have minus b dash over b squared. So if you have 1 over a function, the differentiation is equal minus the differentiation over the square of the derivative. So you have here 1 over Lx. You want to differentiate it. So it'll be equal to what? Let me just first write the constant term, negative lambda square over 2. Now, differentiation 1 over L. So you square L on the bottom, L square, and in the top, the differentiation of the bottom, which is minus, not minus or not? Yes, minus b dash, so minus gl by dx, the differentiation. So just remember, 1 over any function, you will find differentiation is equal minus the differentiation of this function at the top, and the bottom squares of the function. I proved for you. Now, just that's extra. Now we got this formula, just let's make it clean a little bit. So negative times negative is equal positive, and you have lambda square over 2L squared. So you have lambda square over 2L squared multiplied by GL by GX. Well, it's very interesting because lambda square, L square on the bottom, so you can say 1 over 2 lambda over L all square GL by GX. What's lambda over L? Go here. Lambda over L is equal I, right? Lambda over L is equal I. So I can replace this bracket by I. So you have half I square dl by dx. So the force we just found here, it's equal 1/2 I square gl by dx in linear system or linear magnetic system. So you can get the force if you know the current in the winding and the inductance of the system. How can you find the inductance of the system? If you review the practice for the inductance, remember it's L is equal N square over reluctance. Okay, you got to review. I mean, how we get, because I mean the problem. I'm going to give you like worksheet to work. You have to remember what we did before. It's all connected. So that's the force. And if also you try to find it from the other side, because the other equation, which is the force is equal to the differentiation of the coenergy expressed in I with respect to x. If you do that, you get the same result. I'll leave this for you as exercise, but I will refresh your memory how you find the co-energy, it's just lambda I minus WF. That's one case. And then you make the differentiation, you get the force. When you do that, you'll find you get the same answer. You can get the force equal to 1/2 lambda. Sorry. 1/2 I squared dl by dx. You get the same result that you got here.
So basically, no matter which way we do it first, you can do it the other way.
Exactly.
With any problem.
You know why? I'll tell you why. Look at that. Let me tell you that if I was sketch here to ask the question, that's I and that's lambda, and it's straight line. Let's talk about we are trying to get it at I equal 4 and lambda equal 10. Just easy number, 10. The question is simple question. No machines in it, no electricity. What is the value of WF in this one? All right, I'm asking geometry. Give me number. What's the value of WF?
4 times 10 divided by 2.
Exactly. The area of rectangle. This one is rectangle. That's right. 10 times 4 over 2 is 20. So it's equal to 20 joule. What about the area of the co-energy, WC? 20. Okay. So what you get? In linear system, the energy stored in the field is equal to the co-energy. Because straight line. The area of the both rectangle are equal. So that's very important. So in linear magnetic system, WF equal WC equal half lambda I. Just what you did. Both are equal. So that's why you get the same expression. Okay. Let me take one example for what we did. I hope we can do 2 examples, because I mean, there's one here, it doesn't include force, but it's important to understand. Okay. So in this example, it's electro mechanical device here, and it's linear. And we want to sketch L, sketch L of X, and try to find the induced EMF in the excitation coil, the value of E, the voltage produced here for the linear actuator. And this obviously the movable part. Okay. So it's simple. The all information given here, like G, D, L, and all the things given here. We are going to get it like in terms of these variables. All right. So first of all, we need to find the inductance L in the system. So you got to know what is the inductance. How can you define the inductance? What's the inductance? I just remind you by the 1 minute ago, L inductance is equal to what? N square over the reluctance. That's the definition of any inductance. All right. We did that before, proved that before in the previous chapter. And L here is function of X. Obviously, N does not change, it's fixed. So what changed with the X? The reluctance. And that's the air gap here. We call it G, the length of the air gap G in the top, G in the bottom. That's the air gap G and G. They are both, I mean, it's X like our X. All right. That's L. What is the definition of the reluctance? The definition of the reluctance, as you know, that L over mu A in general. But now I want to define it with the air gap. RG equal. What's LG? You got two air gaps, by the way. When you look at any device, you have to look at the total air gap length. You have G in the top here, if you can see it, the top, and G in the bottom. What is G? It's the length of the air gap. So you got the L is equal to 2G. Mu, air gap has only mu naught. A, that's, trick. A, what's mean A? I'm talking about the area of the air gap. What does mean the area of air gap? If you have the space between the two parts like that, you have to find the common area. Why I'm trying to find the common area? Because that's where the flux will be passing through the air gap. So it'll be going through where the core here. So when you look at this part, you'll find that the flux will be in this area. But this area, there is no core, so the flux will not go through. So you find where is the core, the common core, the iron core here, and then that will be the area. So the area, remember the length, or this one D, the depth, and the length is L, and the height is G. So can you find the area, the common area? That's D, and that's L, and it moved, the mobile part, it moved by X. I want to figure it out. Let me just make it bigger here. That's, the D, but this part, when let me sketch, the mobile part, it wasn't the beginning. From the beginning, this edge was here, and then it moved X. So it actually moved up to here. So when we do it, so if you make a line like that, this is, like where the flux will be flowing here. So the area, the common area in the core, I'm just sketching now. This is the area where the flux will be like going through. If this is all D, and it was D from here up to here, but it moved by X. So what's the length of this box? It's D minus X, right? This is D, and this is X. No flux will go here. The flux will be in the air where is the core, want to cross from one core to another. So that length will be equal to G minus X. What about the length of this one? It's the same as this one, and this one is equal L, because it will move like that in this direction to the right. So that's L. So the area will be equal D minus X times L, this rectangle. Can you see it? All right. So I'll say that the area of the air gap is equal G minus X times L. Okay. So now let's go back what we tried to do. Now we want to find the area. So the area is equal to G minus X times L. That's the area. So we found the reluctance. Now I can find the expression for the inductance. So L of X is equal to N square. When you divide, so the top and the bottom will be 2G. The bottom will be in the top, mu naught G minus X L. I would like to keep the all constant parameters outside. So I will have N square mu naught L over 2G times G minus X. I want the term that has X outside. So, and even to make it simple, I'm going to call this K, constant K. So now I can write L of X is equal to K G minus X. And now I can sketch. The first question that was asked, how to sketch L of X against X. The change of the inductance with the air gap when it's moving, it will be a straight line. The first one, when X equals 0. When X equals 0, what's the value? When X equals 0, L of x is equal k d minus 0. So it will be equal k d. I will call this L0 here. So L0 is equal k times d, the constant d. What happened when x equal d? When x equal d, what you'll get? Lx will be equal k, d minus d will be 0, So L will be 0 at x equal d. And then I connect the straight line. So I did the straight line they asked for. That's the equation for that. So when that, what does it mean? This straight line. It means that when x equals 0, it means like, I mean, no space is like no space there. So that's the maximum. And then every time x is moving, L is decreasing till x equal d. What means x equal d? Remember this x, d. It means the whole movable part outside. When the whole movable part just moving outside the magnet cell, no flux can go through. So L will be equal to. All right, makes sense for the equation. So yes.
On the RG, where did the 2G come from?
Because you have two G, G in the top, G in the bottom. You got two air gaps.
Oh, okay.
Yeah, that's good because I mean you will find some problem. We have only one gap, two gap, three gaps. So you got to be careful about that. That's the path of the flux. So we did the first part that we found the relationship between L, the inductance, and the displacement X or the air gap. We need to do the second part. The second part, you want to find the EMF. The EMF produced in this device across this line. So we have to know the basic relationship for the induced EMF. The induced EMF, E, we know it's equal to the change of the flux linkage with respect to time. That's the main equation. Okay. Remember that you can have, if you have lambda I will refresh your memory, lambda I, you can have many, according to the X, for example, that's at X1 and X2, you can have many straight lines according to the displacement or the air gap. So we'll say that lambda is equal L of X times I. I want to find the differentiation of lambda with respect to time. So I will say the differentiation of the first I is constant and the differentiation for the first dl by dt, right? And then I will let Lx constant, the differentiation of di with respect to dt, right? That's I mean how we find differentiation of the product. And dx, oh, by the way, there is something here. How can you get dl by dt and it's variable of x? Let me make this a little bit more clear. dl by dx first you find dl by dx and then dx by dt. You cannot do one time because function of x, right? It's like L of x is equal 10x squared. So first you find the differentiation of L with respect to x and then x with respect to t. And that's already function of time, no problem. What's dx by dt? What's dx by dt? X is the air gap and dx by dt, the rate of change of the displacement. It's the velocity, right? How fast it's moving, right? So will be equal to I dl by dx times the velocity. This is velocity, not voltage. Well, let's take another, call it u, for example. Let's call it u. U, velocity, plus L of x times di by dt. Okay. You want to find dl by dx. How you find dl by dx? You already got the relation, the formula for L of x. That's L of x k d minus x. K d minus x. So dl by dx to find this term is equal to k is constant and differential of d minus x will be d is not function of x, will be 0, and minus 1, so be minus K. That's easy. So now I can write this relation, the differentiation of flux linkage with respect to time equal to I dl by dx, and dl by dx we found equal minus K, so we have minus K I U plus Lx, and even know Lx what it is, but it's okay, di by dt. So that will be the equation for d lambda by dt, which is the E induced EMF. So this relationship can be used to find the induced EMF across the winding when you have a device that there is a fixed or stationary part and movable part, and every time you are moving, it will affect two things: the inductance of the system and accordingly the induced EMF across the winding. So we analyze, this device, thoroughly inside in all details. So, and we'll have examples of problems. Do you have any question? Right. We'll continue. Right.